Hello everyone, welcome back to our NDT training session. I'm Muthulakshmi ASNT Level 3 in 10 Methods, API, PMP and Frozio Level 3 certification holder. And it's great to continue our journey into the world of non-destructive testing. In our previous session, we extensively discussed magnetic flux and flux leakage, understanding how these invisible lines of force become visible indication when disrupted by flaws. Now we are going to dive into electrically induced magnetism, which is the primary method used to create magnetic fields in test object during magnetic particle testing. This topic builds directly on our understanding of magnetic flux and how it behaves around discontinuities. We will now go slide by slide, breaking down how we generate these magnetic fields and making sure everyone clearly understands the essential. Let's go to the session. There are two primary ways to induce magnetism using electricity for magnetic particle testing. One is circular magnetization and longitudinal magnetization, and we often combine them through multi-directional magnetization. First, we discuss about circular magnetization. Our journey into electrically induced magnetism starts with the fundamental principle of when electric current flows through a conductor, a magnetic field forms around it. This is visualized by the right hand rule. Already we know that we already studied in our school days. If your thumb points in the current direction, your curled fingers shows the direction of magnetic flux. This is the right hand rule. The magnetic lines are always perpendicular to the current flow. Imagine holding the conductor in your right hand. Point your thumb in the direction of current flow. Your curled fingers will then show the direction of magnetic flux. This is the current flow direction. This is the magnetic field. So this is your curled fingers, this is your thumb. This rule highlights that magnetic lines are perpendicular to the current flow. So current flow in this direction, the magnetic flow in this direction, in circular motion. When we apply this principle to ferromagnetic test objects, if the current flows through the path, it naturally creates circular magnetic fields. These are also known as circumferential magnetization because the flux loops entirely within the material. This is the material, so this magnetic field covers the entire material, circulating around the current path. Next, we saw the key characteristics of the circular magnetization. First, flux loops internally. In a circular magnetized object, the magnetic flux essentially loops entirely within the material. So, no magnetic poles, no external poles. A key characteristics of circular magnetization is that no distinct magnetic poles north or south form on the external surface of the test object unless a discontinuity crosses the flux line. Next, detection mechanism. This is the crucial for NDT. Magnetic particles will only gather where the flux leakage, meaning they will accumulate at discontinuities. These discontinuities like cracks force the internal flux to leak out, creating those small localized north and south poles we discussed in the previous session. Next, field strength distribution. When electric current flows, directly through the path. Example, a tube. This is a tube. When electric current flows directly through the path, the magnetic flux is strongest out at the outer surface of the path and gradually becomes zero at the center. In center it's zero, but in outer surface the magnetic flux is strongest. This is an important consideration for detecting internal flaws. We move the next slide. Inducing circular magnetization. Now let's look at the common ways we apply current to create these circular fields. First one is direct contact method. This is a straightforward approach where the test object is clamped between contact plates. This is a clamped. The part between the clamp of this is a test unit. This is our test unit, that means our part. The current flows through the part. This direct current flow induces the desired circular magnetic field within the component. Next topic is internal conductor method. This method is primarily used for tubular or hollow components. A conductor like a copper bar or rod is placed inside the tube. Like hollow components means this is the hollow components. This is a empty space. The current then flows through this internal conductor, not through the tube itself. The current then flows through this internal conductor, not through the tube itself. This current in the central conductor induces a circular magnetic field in the surrounding tube, inside the tube. For very long tubes, an insulated conductor is often used along the bore. It is also important to place the tube on the wooden planks or other insulated material to insulate it and avoid arc burns if current tries to find an alternative path. Simple example, to inspect a pipe, you would thread a copper bar through its center and the current pass through the bar. The pipe itself becomes circularly magnetized. So next is magnetic field direction right hand rule. Already we saw the right hand rule. Thumb points in the current direction and curled finger shows the flux direction. Always the magnetic lines are perpendicular to the current flow. So this is the current direction. This curl fingers shows the flux direction. This is the flux, circular field. Next, longitudinal magnetization. In contrast to circular magnetization, longitudinal magnetization creates fields that run along the length of the path. How it's created? Any idea? Okay. Longitudinal magnetization is primarily created by forming a coil through which electric current flows. Now, object inside coil. When a test object inside this current carrying coil, the magnetic field lines align lengthwise. This is a longitudinal magnetization. Inside the coil and through the object. Unlike circular magnetization, with longitudinal magnetization, the magnetic poles typically form near the ends of the object, where the flux line exit and re-enter the material. For detection, we are looking for discontinuities that disrupt this lengthwise flow. First, transverse crack. Transverse crack means crack that runs across the object length. This is the object, this is length. This is a transverse crack perpendicular to the longitudinal field lines. Sorry, this is a longitudinal field line. This is a transverse crack. In this object, this is weld. This is transverse crack. Here our fields are longitudinal field. So perpendicular to the longitudinal field. Transverse cracks will disturb the flux. This disruption leads to the formation of leakage field, which then attract magnetic particles and it forms a visible indications. Next we saw a multidirectional magnetization. We have learned that for optimal detection, a discontinuity must be perpendicular to the magnetic flux flow, as discussed in the previous session on orientation. This means a single fixed direction of magnetization might miss flaws oriented differently. The primary reason for utilizing multidirectional magnetization in magnetic inspection is to detect discontinuities in various orientation. This is the main reason. So we can use both circular and longitudinal magnetization. Instead of applying just one type of field, we apply two or more magnetization currents in quick succession. This typically involves combining circular and longitudinal fields, cycling between them rapidly. As long as these alternating currents continues to flow, all favorably oriented defects will produce persistent visible indication, whether they are transverse or longitudinal or at angle. This allows for a more comprehensive inspection in a single setup. I will prepare some questions for this session. Comment your answers in the comment box. I hope you all now have a solid understanding of how magnetic fields are actually created in a test object using electricity and the different types of fields, that means longitudinal and circular magnetic fields, we can generate. You also know why multidirectional magnetization is so important for comprehensive inspection. If you have any further clarification, comment on comment box. Thank you.